Hi, everyone, and welcome. My name is Aaron Smith, and I'm the CEO of EEBA, and I'm joined by Nancy Bacon, Executive Vice President here from balmy Minneapolis, Minnesota. We're really pleased to invite you to the EEBA webinar podcast series. We've got a great topic and great speaker today. This is Zero Energy Homes. We're joined by our friend Aaliyah German, who is the engineering manager at Frontier Energy and is really going to give us a lay of the landscape on zero energy homes, some of the definitions. I was most intrigued when we set this up about, I think we always want to know what's going on in California, where is policy, where are codes heading. As always, we have the Q&A section at the bottom of the screen. You can enter your questions there. I will curate those and ask them to Aaliyah throughout the presentation. You can as Mike Barsick is doing right now, you can always chat to us and say hello. We will put some links and different things in the chat function as well. But we want to welcome you all. We hope you're staying cool, and we hope you enjoy this great presentation from our friends at Frontier Energy. With that, Aaliyah, I'll turn it over to you.
Great. Thanks so much, Aaron. And hi, everyone. I'm really glad to be here today and looking forward to this presentation. So let's just dive right in. So I'm with Frontier Energy, and just a quick intro for those of you who aren't familiar with us. We're a consulting firm that's national. I'm actually sitting in Colorado today, but all my work is based in California. So we will be talking a lot about California today. And we specialize in energy efficiency and advanced energy solutions and residential and commercial building stock, food service, and transportation. So today we're going to talk about why zero energy is important, what it is, how it can be defined, general approaches to designing and meeting zero energy, and then what California has done and what lessons we can learn from that. So our learning objectives kind of follow that agenda. We'll understand some key concepts of zero energy homes, discuss how the different definitions can really impact performance and how you're going to design the home, look at what is going on in California, and identify key challenges. So why zero energy? Well, it is people and groups and policymakers are motivated for different reasons: reducing utility costs, moving towards energy independence, climate change, sustainability. Grid harmonization, this is a term we're going to touch on a few times today, and I'd like to introduce it to you. It means how we can work towards alleviating constraints on the electric grid due to peak demand and due to a proliferation of PV. So we've got a lot of PV that, as our grid increasingly has more renewable generation, we have a lot of PV that's producing energy in the middle of the day. And then we have a lot of load oftentimes in the evening after that PV load. So kind of balancing that out. And code policies and programs are increasingly looking towards zero energy to meet goals, climate change goals, greenhouse gas goals, etc. So this is a look at our United States energy consumption. So this graph on the left shows total consumption by major end use sector. And you can see about 40% of total energy use is attributed to buildings. That's a lot, about half residential and half commercial. This is from the US Energy Information Administration, EIA. The graph on the right shows a breakdown for a typical home by end use. So this, of course, is going to vary by climate. It's going to vary by vintage of building, size, et cetera, right? But these are what we're trying to target in zero energy home design. And a lot of this, you can see space heating, water heating, air conditioning, a lot of energy use in homes is for space conditioning, making our home comfortable. There's also a lot, and this is the increasing bar here, that is plug loads, our toys, our TVs, chargers, games, all that kind of stuff. So this is an increasingly important component of building energy use that we need to look at more and more. So what is zero energy? Well, at a really high level, zero energy buildings combine energy efficiency and renewable energy to generate as much energy as is used. So if we look at a typical home that uses just shy of 11,000 kWh and 600 therms, we're going to reduce that through building efficiency. And How much you can reduce it depends on your starting point. Is it a new home, an existing home? But you'll be able to reduce it. And on top of that, then you layer your renewable energy system to offset the energy use of that home. What we will talk about most of today is zero net energy or net zero energy. And this net indicates that there's some sort of trade-off with the electric grid. And most homes that are designed to be zero energy are designed to be zero net energy. That is, they are connected to the electric grid and allow some trade-off with it. So building on those ideas, really the critical thing to address first is reducing your building loads through passive strategies, through optimizing your insulation design, selection of windows, reducing interior gains and interior loads. And then when you combine that with good mechanical design, you don't need a complicated mechanical system to build a zero energy home. You can do this with standard off-the-shelf simplified systems and combine that with efficiency. So efficient HVAC, efficient water heating, appliances, lighting, and MELs or plug loads, miscellaneous electric loads. Renewables are, in the residential sector particularly.
Aaliyah, sorry, what are MELs?
Miscellaneous electric loads. So those are those
That's
plug
the
loads.
phantom load, right?
Yeah, all of that other stuff that isn't heating, cooling, water heating, appliances, and lighting. Everything else you have plugged
That's
in.
all my stuff charging in my house, right?
Exactly, yeah. Thanks, Aaron. So solar is usually what provides most of our renewable offset. Solar thermal may offset our water heating, sometimes space heating. And solar PV is what we're going to talk about for most of our zero energy buildings today. And there may be some sites where wind or hydroelectric is appropriate. So how is it defined? There's no consensus on what zero energy is, and different groups define them differently. There's zero electricity, which in a mixed fuel home isn't true zero energy. You're just looking at one of those fuel sources. There's site energy and source energy, and we'll talk about that in a little more detail in a few slides. Utility bill, zero utility bill. If you zero your energy, you're not necessarily zero utility bills. So that's another way to look at it. Zero emissions. This is becoming increasingly important and of interest to many policymakers. Peak demand, so eliminating that demand on the grid during peak times. And TDV, time-dependent valuation. This is a California-centric metric that I do just want to introduce because it does come into play when we talk about what California has done and what we're doing. So it's the California Energy Commission's code compliance metric that's intended to capture the societal and environmental impacts of the true cost of energy at any hour. So it values energy use differently based on fuel type, based on hour of the day, and season. And while these multipliers, TDV is very unique to California, this kind of idea of valuing energy distinctly each hour of the day is really important when we look at electricity generation, where that's coming from, and how that really does differ hour by hour.
And Aaliyah, can you just reiterate what TDV stands for the audience?
Time-dependent valuation.
Great, thank you. And that's where we hear about, I think my friend in Long Beach, California, at 6 p.m. at night, they have a 60 cents a kilowatt hour, because during that hour from 6 to 7 p.m., it's charging the time-dependent valuation, right?
That's right. And so time of use, we do have utility rates that are meant to kind of reflect that, right? Time of use rates where the cost of energy, as you said, is valued differently at different times. More when it's more expensive for the utility to produce it.
Thank you.
Yeah. So the Department of Energy came out with a definition of zero energy in 2015 to try and add some kind of continuity between all these different definitions. And what they're saying is that a building, a campus, a portfolio, or a community is zero energy if on a source energy basis, the actual annual delivered energy is less than or equal to the on-site renewable exported energy. So a few important notes there. Source energy, we'll talk about that next slide. Annual. So when they say annual, that implies net. That implies some sort of trade-off with the electric grid. And one of the most interesting is that they specify actual. So most zero energy definitions are based on an asset rating. So you design a building to be zero energy. Ultimately, what we all want is the actual building to be zero energy during operation, right? But that is more challenging to validate, to verify. But that's what they're implying here, that it needs to actually be zero energy. It needs to be validated that it's zero energy over time. So source versus site. Site energy is the energy use that you see on your utility bill. So if you get a monthly bill that says you've used 500 kWh, 50 therms, that's site energy. That's the energy that's passing through your electric or gas meter. Source energy includes all of the production, transmission, and delivery of that energy from the original source to your site. And it's kind of a more holistic way of viewing the entire energy components of what you use at your house, and a better way to compare different fuels. So this table here down at the bottom is from Energy Star's portfolio manager. And these numbers aren't important to remember, but I just want to point out a couple things here. So different energy types and energy from different sources have different source to site ratios. There's also two columns for the US and Canada. And what this tells us is that it really depends on where and how you're producing, transmitting, and delivering that energy. That really impacts how much total energy it's going to take to get that to the consumer. So natural gas, for example, has this source to site ratio of 1.05. So that means that it takes 1.05 units of energy to bring 1 unit of natural gas to your house. Electricity, on the other hand, is a refined fuel from other sources. And according to this table, it takes 2.8 units of energy to bring you 1 unit of electricity to your house. So you can see with these ratios, it's a really big difference whether you're looking at something from a site energy or a source energy perspective.
And Aaliyah, a lot of that is transmission loss, generation loss, things like that from the grid, right?
That's right. Yeah. So you're combusting coal or natural gas. Those processes have inefficiencies, and then you have to send it through pipelines, et cetera. Transmission stations, all of those involve losses. But depending on where you're producing, how you're producing your electricity, if it's from coal or natural gas or renewables, those have really different site to source ratios, because that production of the electricity has a lot to do with how much energy it takes to produce it. So where does our electricity come from? So this graph on the left is US generation over the last 70 years. So the brown on the bottom is this big chunk that's coal, that traditionally we've had a lot of energy use produced from coal, and natural gas as well. And this has really grown over the past few decades. Nuclear, renewables, and this has just more recently grown, and petroleum and others kind of petered out. On the right side is the breakdown of renewable energy over that same time period. So through most of the time, it's really just been hydroelectric. And just over the past couple of decades, layered on some biomass, geothermal, and then just the last 10 years, wind has really skyrocketed, a lot more utility wind farms. And you see solar kind of eking up there too. So these are going to increase over time, definitely. All right, so I wanted to look a little bit about how these different definitions kind of impact ultimately the design of our Z&E house in terms of the renewable energy component. So I said that most often in homes and buildings, we have a solar PV system that's going to offset the energy use that we're using in our building. So we're going to look at this from that viewpoint, the PV capacity of that system that would be required to meet zero energy. And we have two different building types. So a gas electric, a mixed fuel home is one that has gas for space heating, water heating, cooking, and clothes drying. An all electric home is one that has no fossil fuels, no natural gas, no propane piped to the house. So everything is electric. And then we're going to look at three different ways that we talked about defining zero energy. Now, the first is zero net electricity, which I did say for a mixed fuel home isn't really zero energy, right? And you can see that for this mixed fuel home, you end up with a lower PV system and you're just kind of ignoring the gas component. And then of course you have a larger PV system, 5 kW for your all electric home, because you're offsetting the electricity use of those end uses that were gas in your mixed fuel home. So space heating, water heating, cooking, and clothes drying. And then if we go to zero site energy in our mixed fuel home. So now this is, we're just doing a simple metric conversion from kWh and therms into the same value. We're not taking into account any source factors. The mixed fuel home ends up with a pretty big system to offset that gas use over 8 kW. And then our all electric home, well, it's the same size as in this case because we still just have electricity. Then if we move to the source definition, now we end up with a much more similar comparison between the two. Now, one thing to point out that I alluded to a couple slides back is that this source factor really depends on your electricity generation. So this comparison is going to look a lot different depending on where your electricity is coming from. So, how much source energy do you have to offset? If it's really dirty, you're going to have a bigger PV system to do that. If it's clean, then you'll have a much smaller PV system to do that. So these, you can see how these definitions really impact how you're going to design and size your renewable energy system. And now let's look at greenhouse gas emissions and how these two building types compare relative to this. So this is from E3's Residential Building Electrification in California study that Frontier Energy supported the residential analysis on. And we're going to look at annual CO2 equivalent emissions. Again, we're looking at our mixed fuel home, same type of mix there between fuel and gas, and then our all electric home. And this is comparing emissions from direct, electricity use, refrigerant leakage, because refrigerants have global warming potential when they are leaked in our air conditioners and heat pumps. Combustion of natural gas, when you have gas at the house, and then natural gas leakage. So this is methane leakage in the distribution process, any leakage that might occur at the meter, etc. So a couple interesting things that I want to point out to everyone. One is that there's a huge difference when you look at greenhouse gas emissions between a mixed fuel and all electric home. You get a lot of savings by shifting to all electric. The other is that this is looking into the future. So 2020 today, 10 years out, 30 years out. As we move into the future, there's a couple big shifts here. One is this refrigerant leakage component reduces quite significantly in both building types. And that's because we're anticipating the introduction of low global warming potential refrigerants, which is, pretty critical, right? Because this is a big chunk of this column. Right. The other is that this electricity piece is dropping quite significantly. And that's because the grid is expected to green. So as we get more renewable energy generation on the grid, then there's much less greenhouse gas emissions as a result of that electricity consumption. And so this goes to say that, depending on where you're designing a zero energy home and what the grid looked like and how you're defining zero energy might really impact your renewable energy system that is required to offset that. So I talked about solar PV and having that be on the house. It could be on a roof or adjacent so that it can be easily connected. But how does that really work? So net metering has grown really prevalent. It's essentially a trade agreement with the utilities. And when you have a solar system on the rooftop, this feeds into an inverter, which then feeds into a net meter. Now, when your solar array is producing electricity and your house has a load, it can directly supply that load. So the electrons can flow directly into the house. If you're producing more electricity than you need at any moment, those electrons can flow back to the power grid and they can be used elsewhere. If at any time you are not producing enough electricity to serve the load, say at night when you don't have any sun, then you can pull electricity from the grid. And so this is really what we mean when we're talking about net zero energy, that there's this trade-off that can occur throughout the year. And ideally on an annual basis, if you're looking at it from an annual perspective, you would try to produce as much electricity as you use on an annual basis. And that would be what we would consider net zero energy. So a full net metering agreement with retail rate compensation to the consumer does end up increasing costs for non-solar customers because you're using this grid. You're taking full advantage of being able to supply your home with electricity at night. And if you really truly were to get to zero utility bill, you're not paying at all for it. So that's a great deal for the consumer. So the reality is that net metering, there's a lot of different aspects of these net metering agreements to try and value that more appropriately. So excess generation may be treated differently if you go beyond producing what you use in a year, or maybe even within a month or a day. Different utilities treat that differently. There's what's called non-bypassable credits, which essentially means whenever you're pulling some electricity from the grid, you need to pay at least a little bit of money for that because you are using the utilities infrastructure. There's fixed charges and minimum bills that the utilities use to try to recuperate some of these fixed charges. And then virtual net metering is an important concept that we have in California and is elsewhere in the United States that's really useful for multifamily and commercial buildings, where you don't necessarily need to have one PV system connected to a single meter. You can have one larger array on a building that's connected to a single meter that feeds back to the utility, and then they virtually assign you credit to each of those, say in a multifamily situation, apartment meters. Another type of agreement is what's called a feed-in tariff, where the utility really just pays you a certain amount for any electricity that you send back to the grid, and that's typically going to be lower than retail rate, what you pay for electricity. And I wanted to bring up centralized PV and microgrid scenarios because I think these are going to become more common. There's a lot of regulatory challenges with them now in California. How does it work? How do the credits flow? But I think there'll be some great solutions for this in the near term.
Aaliyah, are you going to talk more about that in future slides? The centralized PV, or would it be a quick question?
Yeah, not a lot, but if there's
okay, well, I think the question generally is, if you're a builder developer and you're looking at doing neighborhood scale projects, what is the potential to do microgrid, to do centralized PV, centralized battery storage? I guess what's your take on the landscape and what regulatory challenges are we going to face as builders and developers?
Yeah, so the real answer is that it totally depends where you are in the utility.
It's all by your zip code, isn't it?
It totally is. We've worked on some projects in California that 10 years ago we tried to do this, and it just didn't work. It didn't pencil out because the agreements with the utility were so onerous and were going to compensate the the developer at such a low rate that it didn't make sense. That is all changing and everywhere, right? And so it totally depends on where you're at. And the first step is really to connect with the utility and see what programs they might offer for something like that, because it does make a lot of sense. From a dollar per kW perspective, installing a system, a central PV system or a central battery system, it's lower to do a central system than it is to do a whole bunch of individual ones.
Right.
And maybe, you know, there could not be great solar access on all the roofs, etc. So there's a lot of benefits to it. And I think we're going to get to where this is more common. But right now it's really just dependent on where you're at in the landscape there.
Right. And Aaliyah, would that be a place where U.S. Frontier Energy could help a builder developer is kind of analyze that for a neighborhood in a community and work with their utility? Not to do a commercial for you, but I.
Yeah, we have, you know, that's what we've done for some of these different communities and looked at, okay, well, you know, this you have to look at the different rate structures, right? Like
Right.
what is going to be the benefit? How is this all going to play out? And so, yeah, all those things can be evaluated.
Great, thank you for that.
Yeah. So back to that idea of grid harmonization. So this is what has been known and coined as the duck curve. You can kind of, you know, if you imagine it, use your imagination, see the duck is like the belly sloping down and then the head coming up. And this graph on the left is what the California Independent Service Operators, it's the California ISO is the group that operates the electric grid throughout California.
Leah, this is the famous duck's back, right?
Yes, yeah, exactly, yeah. So this is what they predicted in like 2013 or 2014. This graph on the right is from just a few months ago. So what this is showing is that in the middle of the day, you've got all this PV, you know, both utility grade and on rooftops, and it's you know, reducing that total load. So this is megawatts total load by hour for a day. So across all of California. So you've got really low total load in the middle of the day because of all this PV. There's even an actual risk of over generating. You don't have load to push off that generation for. And then the sun goes down and everyone gets home and turns on their toys and turns on the air conditioner. And you need to ramp up 13,000 megawatt hours in 3 hours. And
how many power plants is that?
It's a lot.
Right?
I mean,
so that's where your peaker plants are coming online. I mean, exactly. You're having to bring a tremendous amount of electricity online during those evening hours.
And those peaker plants are usually are less efficient. So that's where that hourly valuation of greenhouse gas, of source energy really comes into play, because it differs for all these hours, right?
Sure.
So, I mean, this is really happening. This is just earlier this year, almost 14,000 megawatt hour ramp. So this is really hard for grid operators to manage.
Yeah.
And so there's a lot of focus right now in California and everywhere on load management. So, you know, this is batteries, both utility scale and in the house. This is thermal storage, pre-cooling, using thermal mass in the home, load shifting with electric water heaters, etc. So load shifting is
we had some questions on acronyms. So HPWH is heat pump water heater, and using that to load shift. So if you think about pre-cooling, have your air conditioning cool your house before 4 p.m. instead of having it cool more at 6 p.m., right?
Exactly. Yep. Right. Yep. Shift that time. Yep. Same thing with the water heating. Mm-hmm. Yeah. Thanks. But one other design aspect I wanted to touch on was behavior. It's one thing to design a zero energy home and we make all these assumptions for how we're going to operate the home, what we're going to bring into it, et cetera. But then occupants come in and they do all sorts of things. And that's the beauty of human nature, right? So this graph is from UC Davis, West Village. It's one of the first zero energy planned communities in the United States, and it's been operational for a few years now in California. And this graph shows, you know, the number of homes that this is based on monitoring. So a couple years after occupancy, we monitored the energy use of these homes of different units. This is multifamily housing, and compared that to what we modeled. And so, 100% means that there was about 12 units that actually were, really close to what we estimated. Not bad, right? But then, down here, there's a whole bunch down to 50%, and then a whole bunch more up to 150%. So this is really hard to deal with. It also means that it's much more challenging to meet zero energy on a single building than a community because of this variability. If to the point of someone who asked this question about kind of microgrid, that kind of flattens this out a little bit, right? When you can install these renewable systems on a community that offset the energy use, then it's a lot easier to try and meet your zero energy goals than it is on each individual house.
Sure,
So,
because of the variability of each user, right?
exactly, right. On a house by house basis, if somebody uses more and the next person uses less, they're not trading that off between each house, but you can do that with a central system more easily. So education, engaging, empowering occupants. Now, I don't think that a occupant really needs to live any differently in a zero energy home than they would in any other home, but an occupant understanding their home and understanding kind of the implications of their behavior is important to push zero energy into the forefront.
Mm-hmm.
All right. So Aaron, we're going to shift to this California discussion. Is there anything any questions that we want to address before we do that?
One question was just in particular to Florida, and I don't know if you have an answer to that, but are you aware of homeowners having a problem with insurance when they add, and they're saying when they net meter, but I actually think they mean when they add solar or PV to their house.
And maybe is that specific to kind of storm season, storm issues? And
that would be my take, because Jeanette is asking that. That was from Florida.
I don't know. I don't know the answer to that specifically in Florida. I know that there's a lot of solar on homes in Florida for sure, and it's a great state for solar access. So I would think that there is some solution for that, at least in many regions.
Right. I think that's the pertinent questions for right now. Some will save to the end.
Okay. Sounds good. All right. So we're going to talk a little bit about what California has done and where we're going. And I just want to introduce you to a few policies that are kind of pertinent to give us some context. So there's Assembly Bill 32 that required the state to reduce greenhouse gas emissions to 1990 levels by 2020. And we did it. So this line here shows that 1990 level. And this is measured greenhouse gas emissions statewide. And around 2016, we actually dipped below it and have stayed below ever since. So the next step is getting 40% below those levels by 2030. So that's kind of where a lot of our policy is heading. The long-term energy efficiency strategic plan set a goal for residential new construction to be zero net energy by 2020. We didn't quite make that, and we'll talk about that. Right. And there's still a goal for commercial new construction to be ZNE by 2030. The renewable portfolio standard sets requirements for renewable energy generation across the utilities that provide electricity throughout the state. And the initial goal was to meet 20% from renewable energy by 2017, and we easily met that. This graph here shows it's an average across the year, which is kind of interesting. Total hourly generation by hour. So of course, this is going to look different in December than July, and this is kind of an average of all those months. And you see a lot of this is all solar, so there's quite a bit of solar on the grid. There's base load here, geothermal, biomass, nuclear, and wind, and hydro, of course, and then natural gas. We don't have much coal, but we do have a lot of natural gas in California. And imports. Imports are a mix of renewable and non-renewable energy.
And that the imports are energy you're pulling from the grid in Arizona or Oregon.
Exactly.
Or Washington.
Yeah.
Got it.
Yeah. Importing from other states.
Yeah.
Mm-hmm. So the next step is to meet 100% renewable by 2040. So that's where a lot of policy and goals are moving towards now. So how does California define ZNE? We're just as confused as everyone else. So on the left is the Department of General Services adopted this definition for their state buildings. And it's the DOE definition. So they just adopted the DOE definition, which says, on a source energy basis, actual annual energy shall be less than or equal to on-site renewable generated energy. So that's pretty straightforward. On the right is the California Energy Commission's definition from a few years back now, and it's not codified, and it's really confusing. And I expect that there's going to be some movement around relooking at this again, especially now incorporating a shift in prioritizing carbon emissions. So what this says is that a ZNE code building is one where the societal value of the amount of energy provided by on-site renewable energy sources is equal to the value of the energy consumed by the building annually at the level of a single project seeking development, entitlements, and building code permits measured using California Energy Commission's TDV metric. That's that time-dependent valuation. Right. So that's, no builder, no implementer is ever going to understand that. But the key is that they've been really focused on asset rating. This isn't talking about actual energy use. It's talking about a code building, a building designed to meet these standards. TDV, it's proposing to use this time-dependent valuation metric. And again, that might be shifting here, but what won't be shifting is this valuation of energy distinctly at different hours, because that's really important, as we've seen in some of these other slides, to properly kind of value where your energy is coming from.
Right. And I think the key thing in there, maybe, Aaliyah, is the societal value, which allows California to account for those emissions, not just in terms of pure kilowatt hour, but also in terms of carbon emissions exhausted, right?
Yeah. No, that's a good point. That's a great point. Yep. Societal. Yep. That's what's fed into this TDV metric, and it's been really important.
It's almost that environmental social governance investor model, but looking at all energy sources from that standpoint in California, right?
That's right. Yeah. Exactly.
Great. Thank you.
Yeah. So California has had a building efficiency code since 1978, which is a while. Every 3 years, we update the code, and any provisions that get added must be demonstrated to be cost effective. So it's a pretty rigorous process. And I wanted to just highlight a couple of aspects of the last few code cycles. In 2013 and 2016, we made some really amazing strides with efficiency. There was a lot of efficiency that was added into the codes for residential buildings, particularly. 2019, there was more efficiency, but the big thing was adding a PV requirement for new residential homes, single family and low-rise multifamily. And next slide, we'll talk about kind of what that requirement is. And so today we are under the 2019 code. It went into effect January 1st of 2020. So we're about halfway through it. We are in the process now of developing the 2022 code, which will go into effect in January 1st, 2023, and should be adopted in a couple of months here. So we know pretty well what it's going to look like. And now there's a big push for electrification. So substituting out gas appliances in buildings, residential and commercial, for electric appliances. There's also a lot of building efficiency added to commercial buildings, and both PV and batteries, on-site PV and batteries for many different commercial occupancies. So what does the California Code Home look like? This is under today's code. It has high performance walls, 2x6 with exterior continuous insulation, dual windows, low E coating, insulated doors. This concept of high performance attic, which in California we build vented attics and we always put our ducts in them, which isn't the best location. And so this idea of a high performance attic is to, in addition to putting insulation at the ceiling level, also put insulation at the roof deck level, either above or below, and then that kind of tempers the conditions inside the attic and reduces the loads on the ducts. So either do that or place all your ducts in conditioned space. A whole house fan in many of our climates, LED lighting, a lot of third-party verification of insulation and mechanical systems, and then a PV system that is sized to offset the electricity use of a typical mixed fuel home. So it's sized to offset electricity for everything except space heating, water heating, cooking, and clothes drying. So not quite didnt, and we'll talk about why next slide. The last thing they did is they made a compliance path for all electric homes. So they said mixed fuel homes are compared to mixed fuel homes, and all electric homes are compared to all electric homes. Prior to this code cycle, all electric homes were penalized using the code metrics. And so this was kind of a big step to encourage electric homes. So why didn't we make it to didnt? Well, the big reason is mixed fuel homes. It's one thing to calculate the PV capacity that you need to offset gas use of a home, but there really is no practical way to do that. You are not allowed to overproduce with PV based on, most utilities' net energy metering rules, because they don't want you just pushing a whole bunch of additional PV onto the grid that they have to, then manage and deal with. And even if they did allow you, they're not going to pay you retail rate for it. So the cost effectiveness of that is really challenging. So the Energy Commission, the California Energy Commission in this code cycle wasn't really ready to advocate for full electrification of buildings. And they really wanted to focus on enabling all electric homes. And there's a lot of negotiation with the building industry. And so this was kind of the first step compromise that was landed at. That, requiring PV on every building, residential, single family, low rise, multifamily is a pretty big step. And we have a lot of rooftop PV in California now because of that, but we didn't quite make it to didnt by 2020. So where are they going next? Well, the next step is to really push for all electric buildings. So now they've moved back to a single fixed fuel prescriptive pathway that has either a heat pump for space heating or water heating. You can still build mixed fuel, but you have to make any gas appliances you install, you have to prepare them to be able to install an electric appliance in the future. So there has to be electric infrastructure. For water heaters, there has to be a condensate drain for heat pump water heaters, etc. And then they introduced the new source energy metric, which really kind of validates the fixed fuel pathway and encourages electrification. So if you install a gas appliance where prescriptively a heat pump is required, you get a slight penalty in most climates, and you have to make that up. If you instead install an electric appliance where a gas one would be prescriptively allowed, you get a slight compliance benefit. So the intent is to kind of take that next step and encourage electrification while not requiring it. And there's no change in the PV size requirements, at least this round. So how has this really impacted energy use in California? And these are some really interesting graphs. So we'll start here on the left. This is, our y-axis is electricity per capita, so kWh per capita, over the last 55 years or so. So here's the United States compared to a whole bunch of other countries, and then the world as a whole. And you can see the US is much higher than at least all these other countries that are being compared against in this graph. Then this center one is the United States less California compared to California. And this is really interesting. Starting around 1978, late 70s, 76, when the energy building efficiency code went into effect, the energy use per capita has pretty much leveled out. Now, there's been a lot of studies that have looked at, can we attribute this to policy, et cetera, and it's kind of up in the air. But the end result is that, a combination of things have contributed to this flat line. So then if we look at this graph on the right, this compares, so here's California, that same line against all these other states, South Carolina, Texas, Ohio, Colorado, Massachusetts, and at least over the last, decades, California is lower than the rest. But there's some interesting trends here too, right? South Carolina does a pretty deep dip. Ohio dips too. What's driving that? I'm not sure. I'd be interested to know what policies, or maybe it's not policies, but what is going on in these states to create this. So this can be a good tool to kind of understand how what's going on in individual states and country to country. So aside from, I work a lot on code development in California at the state level, but also with local jurisdictions. And in California, there's a lot of local governments that are making local amendments to their building code, and they're doing this to address policy goals such as climate action plans that they may have. And within our state code, there's an explicit allowance for this, and it requires, just like our state code requires, a cost-effective determination. Historically, there haven't been a lot of jurisdictions that have done this because state code is pretty strict, and it's a decent amount of effort to be able to go through the process and adopt this. But the last 2 years, there's been a lot of interest in them, and we have today about 45 jurisdictions with an approved ordinance, and that number is increasing. And they almost all have exclusively focused on electrification, with many also including additional PV requirements above what code already requires. So it's kind of two flavors that jurisdictions have adopted. And a jurisdiction is, it's a city or a county or a local government group of some sort. And so these two flavors are what we've been calling electric required or electric preferred. So in the electric required case, it requires that certain building occupancies, residential is the most popular, but there's a lot also focus on certain commercial occupancies too. That those occupancies, new construction has to be electric. You're not allowed to build mixed fuel. The electric preferred approach is you can build mixed fuel, but it sets a higher bar. So if you build all electric, you just have to meet state code. If you build mixed fuel, you have to meet a pretty high bar that would include a lot of efficiency, probably mechanical and envelope, or a combination of additional PV and batteries. So a decent amount of additional efficiency or systems beyond what code requires. So this has been really, really powerful in California, and has really shifted the landscape.
And Aaliyah, we're seeing that go to other countries as well.
Yeah, we definitely are. And especially where, there isn't a state in areas where there isn't a state code, and there's cities that have an interest in developing their own codes. And so they have done something really similar and kind of established, their own requirements related to this. Mm-hmm. I just have a couple kind of wrap up slides here. So barriers, fuel selection really is a challenge to zero net energy. It really impacts how you're going to design your home and how you're going to offset your energy use with a renewable energy system. There's regulatory challenges related to net energy metering. There's going to be a lot of changes to utility net energy metering agreements over the next few years and over the next decade, as there's more PV, both at the utility scale, and we see more PV on individual buildings. And so
when you say changes, Aaliyah, that we'll see more net energy metering?
Well, I think we will start, the trend nationally is going to be probably to see more net energy metering agreements in utilities, service territories that haven't had them before. Where we're at, what's going to happen after that is kind of where we're at in California, where we've had NEM for a while, and we're now at NEM 2, which is kind of this remake of NEM, net energy metering, and they're working on NEM 3, which is going to be another redesign of the model to be able to better kind of value the true costs that the utilities have to bear when a customer has solar on the roof, and with trying to still encourage customers to do that. So I really don't know where it's going to land. It's probably a couple of years out, but I think that's kind of the long-term trajectory, is that there's going to be eventually less value in the compensation for rooftop PV, just because if everyone had rooftop PV and everyone was zero net energy and nobody paid any dollars to the utility, they wouldn't have any revenue.
So there's been a lot of questions about that when you get to more and more advanced grid with more PV and more renewable, you have this negotiation between utilities and citizens, right? And that's kind of what any free is. We have to, they still have to deal with all that solar going on the grid.
Exactly. Yeah. And there's different challenges for the utilities, whether they're dealing with it at the utility scale, at a power plant, a solar power plant, or if they're dealing with it at the neighborhood level. They have to make sure that there's sufficient capacity at the neighborhood level. If there's solar neighborhoods where everyone has solar on their roof, and so there's similarities and differences to how they deal with that. And as the utilities, and you saw that in California, there's a requirement that the utilities eventually reach 100% of their generation from renewable sources. And we're seeing that across the country. A lot of utilities are looking at that, or already are pushing towards that. And so as we get closer to those goals, there's going to be less and less interest in having individual rooftop solar systems. And ultimately we're going to end up with a balance, right? I mean, there's a lot of rooftop solar going up now, and that's going to continue. And that is a good strategy in a lot of areas. And there's going to be more utility scale renewable PV systems going up too. And we're going to land somewhere in the middle with that, with the balance of them. Where exactly we'll land, we don't know. Mm-hmm. So related to that, I mean, we kind of talked about this whole, the challenge of kind of balancing that PV and then the consumer loads, that summer afternoon peak, and how to balance those. So there's a lot of utilities now are offering incentives for customers to install batteries. They're also installing batteries at their power plants too, so that they can better manage that PV production. And so that's another area where there's going to be a lot of change in the next decade. And battery costs are dropping drastically. And there's other storage technologies too, beyond just batteries as well.
Sure. I think all of the shifting strategies you talked about are valuable here, right?
Yeah, right, exactly. So education, we talked about that a little bit with behavior and engaging occupants. So the next steps is electrification, that fuel selection barrier. There's been research that's looked at that and has found that the lowest cost, simplest strategy for buildings, at least, is just to electrify it. It's easy, the technology is there. There's more energy efficiency opportunities, and there's a lot of research working towards that. Grid harmonization and load shifting, we talked about that. That's going to be really important. And community solar, right? Our microgrids are kind of somewhere in between that utility scale and rooftop solar. I think we'll start to see these pop up more. And we've primarily talked about new homes, but a lot of these concepts all apply to any building, right? And existing homes are the next frontier that we really need to focus on. It's a bigger challenge. This is a lot easier to do in new homes because you're starting with a clean slate. It's absolutely doable, but certainly more challenging in existing homes. But that's what we need to focus on next.
Can you talk about that in terms of, we have a question that came in from, and it says, you all in California are lucky. Of course, Aaliyah's in Colorado and I'm in Minnesota, but we're both in the Excel territory. But she's in Montana, and they have some challenges with their legislature around not being supportive of solar. But talk about, I mean, there's still, and I could talk about my solar system on my house, but there's still incredible incentives to solarize to move to energy efficiency, even if you have a legislature or a local utility that is not. Is that correct, or is that a fair assumption?
Yeah, I would agree with that. The federal tax credit just got renewed for a few more years, and we'll
That's
see
that,
if it's
and that's at 26% still, right, Aaliyah?
it's at 26%. Yeah, until I think for a couple years.
Yeah.
In 2023, it starts to scale down, and then it's expired in 2025. But it may get extended again. That's for PVs, and it's also for batteries too.
Right.
Um, I mean, even if you do, if you have lower cost electricity, then it does make the cost effectiveness equation more challenging, but you're still offsetting. I mean, in pretty much any scenario, um, except for some, there are some utilities that really just don't allow it or don't give you any benefit. But in most cases, you're going to reduce your energy bill. So there are real monthly savings for installing renewable energy.
Yeah, absolutely. And the 26%, I mean, I would say if you're in Montana today and you're looking at it, it might, I put 14.4 kilowatts on my roof, it cost about 38,000. My utility bill was $160 a month. Now it's zero. I got 26% of 38,000 back on my taxes, which is about 12,000. What did it cost me to put solar on? Technically nothing. I just changed my spending from leasing power to owning power. And then that same analogy applies with batteries, right, Aaliyah? That I think we're reaching that break even point where instead of a whole house generator, I may decide to put battery storage in my house and make it more resilient.
Yeah, that's right. And it's a little more challenging with batteries well, it's definitely more challenging to make it pencil out just because they are more expensive,
Right?
but they're dropping significantly every
Yeah.
day.
It's kind of that same, it's kind of that same Moore's law that we saw with solar panels, right? Where
Yeah.
solar panels have dropped so much in the past 10 years.
Oh, yeah.
Now we're seeing batteries drop incredible amounts every year, year over year.
Right. Yeah.
And now you
And
can plug your car into your house and power your house off your car.
right. And vehicle manufacturers are getting into this idea of using that battery in their
Yeah,
EV as, kind of a home battery to allow for load shifting and communicate with the utility. So that's
right.
just
Yeah,
great.
that would be a bi-directional charger station in your house where you now have portable batteries that you can replace every 3 years, like your car, and power your house off of your car as a backup.
Right. And it serves as your car. So
Right.
it'll be interesting to see where we end up with in batteries and
Right.
homes and buildings, and if um, there we're definitely going to see a lot more in utility scale systems, and we're definitely going to see this whole EV battery bidirectional connection, um, and how many standalone batteries we end up seeing in homes. We'll see. This market's just changing so much. Yeah.
Yeah. It's exciting times.
Yeah, well, this is my last slide here, and looks like
Yeah.
we have a couple more minutes. Are there more questions?
Yeah. I think one great question is why hasn't there been more resistance to utilities not allowing net energy metering?
Hmm. Yeah, that's a heavy question. It's a
It
good
is, right?
good question, and again, that's really has depended place to place, right? Some states or some utility territories have been really challenged with that, where if there aren't where there aren't regulations at the state level to manage that. In some areas, utilities have really just kind of been able to do, what they want to do, and so there hasn't been. It's been challenging to resist that. Other areas where there are state regulations, those have developed and advanced as solar and renewable has come into the forefront. So these models really didn't exist, maybe 2 decades ago. I'm not quite exactly sure the history of kind of all these regulations developing, but they did have to develop. state regulations did have to develop to allow and encourage utilities in some areas of the country to do this.
Yeah. We have a building science question for you. I'll warn you in advance.
Okay.
But, back to the code in California. So you're insulating the roof line and insulating the ceiling to, I assume, temper heat gain into the attic space. Has this benefit been modeled and studied extensively? Like, it seems like continuous insulation along the exterior roof line would be better, or a kind of a room and attic truss that's all insulated and allows space inside the envelope of the conditioned side of the building would be better. So, and what about radiant barriers at the attic space instead? How did California come to that idea of double insulation? Is that climate specific, or what happened there?
Great question. And we probably, Aaron, we need to set up a whole nother hour webinar for that one.
Yeah, right.
But I mean, the short answer is that it has been modeled and evaluated.
Okay.
Extensively is up for debate. It is climate specific. I am not sure if it is appropriate for the rest of the country. Humid climates, very cold climates. It is prioritized in California for our very hot and dry climates. And yeah, there's other ways to do it, which many people would argue are better. If you just, build a conditioned or indirectly conditioned attic, then you have that space to use. Right. Or if you just move your ducts in the conditioned space. There was, for whatever reason, and this is different in the nation, across the nation in other states, but there has been a lot of resistance to conditioned attics and ducts in conditioned space in California. So this was a solution to try and address loads on ducts that are in attics. And it's not perfect, and it's definitely not for all climates, but it's where we're at now.
Yeah, no, it's an interesting take. I think that Indoor Air Plus 2.0 is moving toward all ventilation is inside the building envelope. And again, you'd probably be better served cost-wise to insulate the entire attic and bring that attic into the conditioned space, keep all the vents inside of that space. But
yeah,
model it out for your project.
Yeah.
Great. Well, let's see if we had any more questions come in. No, and Jeanette, I apologize. I don't know exactly your question on the specifically net metered and the insurance issue in Florida. My advice would be to get with the local solar company and see what they know about it. We don't have specific expertise around Florida, so thank you for that. Well, great. Well, Aaliyah, I just want to thank you so much for joining us today. It's been a great presentation. I think that my apologies to some of the audience that I know we use a lot of acronyms and we tried to spell those out each time. We need an acronym Bible as we go into each of these, but you're welcome for teaching you some new acronyms. We apologize for not defining each of those during our presentation. But I just want to thank you again. I want to thank our entire audience. And Aaliyah, love to have you back and talk more about what's going on in California. Because I think you're such a harbinger of what's potentially coming to the rest of the country or different municipalities. And
yeah, so I think thanks for having me here, Aaron and Nancy, and thanks everyone for attending and your questions. And my email is up on the screen. If anyone has further questions or wants to reach out, please feel free to do so. I'd love to have a dialogue with folks.
Great. All right. Thanks so much.
Thank you.
Bye, everyone.
Bye.